Alright, so today we're going to look at unsteady state diffusion for the first time. So what we're going to call it is modeling unsteady state diffusion into a semi-infinite slab. And the reason why we're going to call it a semi-infinite slab and why that matters will become important later on. We'll discuss that. So basically our scenario, if we're going to draw a picture, it looks like this. We have some incredibly long film that stretches out to infinity, and on the left hand side we have some initial concentration. And on the right hand side we have another concentration, whatever concentration we'll have after diffusion occurs for essentially an infinite amount of time, because it's an infinitely long, thin film. Okay, so again, these are the general steps we use whenever we model any situation in transport phenomena. So step 0, draw a picture. I've already done for you. Let's start again with the diffusion convection equation. So again, by now you should be well familiar with this equation. We're going to model a generic species A. A is going to be the only thing diffusing in this system. There's no B, C, or D. Don't worry about those. Just any species A diffusing across this semi-infinite slab. So because there's nothing else happening here, we assume there's going to be no reaction that occurs within the system. And similarly, because it's a slab, we assume that it's going to be rectilinear geometry. And to simplify the problem, we're going to assume that the diffusion will only occur in the z direction. So this is basically already drawn in the picture. It's one-dimensional. The only way the molecules are going to move is along the thin film. So in the z direction, there's no diffusion that we're worrying about in the x or y directions. As always, our second step is going to be writing the total flux equation. So by now you should also have this down pretty well. We're going to use the definition with the mole fraction of A as well as the total flux, which is also going to be for A, but it doesn't matter. To simplify the problem, for now we're going to neglect the advection term. So we're going to say that perhaps we have dilute enough species A where we don't need to worry about, advection grossly affecting our results in this problem. And here, I guess the other definition would make more sense because, the only thing here is really A, so you'd have to consider the solvent as well, but it doesn't really matter. So now we'll combine our results from the total flux equation as well as the diffusion convection equation with Fick's first law. So Fick's first law says that it's always going to be the gradient, negative d the gradient of concentration. Since we're working in one-dimensional rectilinear coordinates, that's just going to be d dz. Now if we combine that with our diffusion convection equation up at here, since Na equals Ja and Ja equals this from Fick's first law, all we need to move is this directly into there, and we'll get the following expression like this. Pulling out the d and the negative sign, because they're going to cancel out, we get what is referred to as Fick's second law. So it's just kind of neat that this is called Fick's second law, but it's not really that important because unlike Fick's first law, which we use in every single problem, Fick's second law is something that we just arrived at directly from the continuity equation, or the diffusion convection equation rather. So we don't really need to invoke it ever. It just comes up whenever we need it. Alright, now things get a little dicey. Now we actually need to solve the indefinite integral, or solve this differential equation. So at this point, the transport problem is over, or the modeling problem is over, and now this is just going to be a mathematics problem. So if you're just concerned with the results of the, mathematics, you could speed ahead in the lecture to only derive the concentration profile, but if your professor wants you to know the full derivation with all the mathematics, keep watching. So the trick for solving was come up by Boltzmann, I believe. Several others actually failed in trying to come up with a solution. Boltzmann, I guess, just played around with it for so long that he actually figured out that this would work. So most of this is going to seem arbitrary because it only works because it works. That Boltzmann knew that this particular way was the way to solve it. There's no real logic in figuring out how he knew that this was the way to solve it. But the trick is to introduce a new variable that we're going to call lambda, and it's going to be z over the square root of 4 dt. Again, this is going to seem completely arbitrary where this came from, but it's the only substitution that makes things work out. So we're going to be trying to incorporate this new variable into our existing differential equation. The way we're going to do it is that the first thing we're going to use and abuse is the chain rule. And the chain rule says when you have z as a function of y and y as a function of x, what it allows you to do is express dz dx as the product of dz dy and dy dx. The way we're going to do it is we're going to say, okay, on both sides of the equation we have a dc dt or dc dz, and we have the lambda that's a function of z and t. So we're going to say, okay, suppose that concentration is a function of lambda. And then we know that lambda is a function of two variables, it's a function of t as well as z. Then using this chain rule definition, what we could do is we could get expressions for dc dt and dc dz, right? From the exact definition from here, you can see that we could express dc dt as the product of dc d lambda dt and dc d lambda dz. And since we have an explicit function for lambda, what I'm showing here in red and blue, the dc d lambda dt and d lambda dz, we could actually do the calculus and solve directly for what those expressions are actually going to be. So that's what I'm going to do. So again, here's our definition of lambda. So in the d lambda dt, if we take those partial derivatives, what we're going to get is that first I pulled out the constants. Remember, if you're taking a partial derivative with respect to t, z is going to be a constant, so I pulled all the constants out of this derivative operator, and the only thing we're going to be taking the derivative of is t to the negative 1/2, which is something that you should be pretty good at taking the derivative of. So that's going to be negative half t to the negative 3/2. You can now put a square root of t down in the denominator and leave one remaining 1 over t out here, and you'll see that we could again group this back together to be lambda, so we're going to get negative half lambda over t. Similarly, on the other side, it's actually super easy, because again, when you're taking the partial derivative with respect to z, t is going to be constant, so it's pretty much going to be z times the constant, and the derivative of z is going to be 1. So that side will be super easy to take care of. Now, looking back at these chain rule definitions we have, we're going to substitute these new expressions that we found back into our chain rules. So over here with the red, the d lambda dt, and over here with the blue, the d lambda dz, we're going to get these two expressions. So literally just plugging this red in from here to here, and this blue in from here to here. Okay, but unfortunately, if you looked back at our original differential equation, this is the second derivative, d squared c dz squared. We only have dc dz, so we need to do a little bit more work on the right hand side of the equation to get that to work out. So what we're going to do is we're going to say, okay, well, to get the second derivative, we're going to need to take the derivative of the first derivative. Okay, and what that's going to do is it's going to be like this. We're going to substitute this in here because that's what we just found, and we just make it a little bit more apparent. So that one in here, we made that substitution. And then, because this doesn't have a z dependence, we can pull this out of the derivative, and the only thing we're taking derivative now is dc d lambda. Now, here is where things get a little dicey, right? You're going to be taking the derivative of dc with respect to two different things, d lambda and dz. This is a little bit of obscure trivia, but it's actually super important from when you took multivariable calculus. We're going to invoke the use of Clairaut's theorem, which says that the cross partials are equal. So if we're taking the partial derivative of c with respect to lambda, it's the same as taking it with respect to z and then lambda afterwards. It doesn't matter which order you take the partial derivatives. They're going to be equivalent when you do it out that way. What that allows us to do is it allows us to, instead of taking the derivative with respect to z, it allows us to take the derivative with respect to lambda. And you'll see the reason why we want to do that momentarily. So we're taking the derivative with respect to lambda of dc dz. And the reason why we want to do that, right, is because we already have this expression up here, right? So if we take the derivative of this with respect to lambda, that's super easy because there's no lambda dependence in the function. It just means that we're going to be taking the second derivative of c with respect to lambda. And now we're going to get, again, this term over here. So if we're subbing that back into the line above, I guess I'll indent it like this. Maybe that makes it more clear. We substitute that line back in. What you'll see is that we get 2 of these 1/4 square root of dt's, and we can multiply those together to just get 1/4 dt. Okay. So to recap what we've done here, we had a differential equation that we didn't know how to solve. We introduced this new variable, lambda, that had this form. And after a little bit of chain rule and Clairaut's theorem, what we found is that the left-hand side could be expressed like this, and the right-hand side could be expressed like this. If we combine those together back into our differential equation, what you'll see is this mess here, which at first glance doesn't look so great, but we could clean it up a little bit, and that'll help a bunch actually. So cleaning it up, we're going to move everything to one side. So I've kept this as the positive side. I've added this over. The d's here will cancel out. So that's good. So you see 1/4t over here. Over here, this will become positive. So there's going to be lambda over t. Well, I guess I kind of spread out those constants. Well, not constants, but you know what I mean. Once you do that, you can multiply this 4t over so that this term doesn't have anything in front of it. And you'll see that the t's will cancel out, and the 4 will at least partially cancel out the 2. So that the final ODE that we have to solve is in this form. If you don't like Calc 4 or differential equations, this might not seem that fantastic to you, but you'll see in a second. So this is the miracle ODE that we get when we use Boltzmann's, substitution of that variable lambda into the equation, which now is possible to solve, and it's actually pretty easy to solve. If you don't remember how, if you fell asleep in differential equations class, you use the substitution that u is dc d lambda first, and what that does is it makes it a pretty easy differential equation to solve. Alright, so this is just going to be the first derivative now, and that's our variables there. So now we're going to put them on opposite sides of the equation again, and now the path should be rather clear to you. So now it's a separable differential equation, so move the u's to the left hand side and the lambdas to the right hand side. Do the indefinite integral, and what you'll arrive at is the log term on the left and this lambda squared over here, because the 2 will cancel out when you do lambda squared over 2, and you get this new constant. Putting everything in terms of exponentials instead of logs will get you that there. Then we need to remember that our definition of u was dc d lambda, and we need to do the second integration to get our general solution. So at this point, we have the general solution to our differential equation. So we have a generalized concentration profile. So we're almost there. The only thing we need to do now is we need to figure out what to do with these constants. So the way, I guess I'll explain this, is that there's something in mathematics that is called the Gaussian error function, and it looks like this. It looks similar to what we see in this equation, but not exactly like what we see in this equation, right? We don't have this 2 over square root of pi. But the Gaussian error function has the following behavior. If evaluated at 0, it turns out to be 0, and if evaluated at infinity, it turns out to be 1. The reason for this prefactor, this 2 over the square root of pi, is that if this turns out to be 1, right, then whatever turns out in the integral must be pi over 2, so that it multiplies by this and turns out to be 1. The actual reason why it equals 1 is because this is what we call normalization. This is actually what you'll see for the common bell curve or normal distribution. That's where this shows up, interestingly enough. Later on, you'll see when we're actually doing problems using the error function, we'll be using pretty much the normal distribution table, because otherwise we can't actually really solve this integral well without an integral table with the I guess the approximations in there. Okay, so taking that into mind, let's look at boundary conditions. So step 6. So the first boundary condition is that back in our original problem, at some time greater than 0, we're going to have this initial concentration on the left-hand side of the slab and this concentration on the right-hand side of the slab. So at least the boundary conditions are pretty simple in this problem. Probably the only thing that's pretty simple. So remember, concentration now needs to be a function of two variables. It needs to be a function of t as well as z. So when t is greater than 0, we're going to have that concentration there, that initial concentration at the left-hand wall, and when time is greater than 0 at the right-hand wall at z equals infinity, we're going to have a second concentration that we'll designate that way. So since I've told you that the error function turns out to be 0 when evaluated at 0, and this integral looks pretty much the same, what you'll see happen when you evaluate this function at 0 is that this integral will go to 0. So on the left-hand side, our concentration is just going to be the initial concentration. This integral will go to 0. So we see that K1 is simply going to be our initial concentration. Taking that into mind, I've updated our general solution. I just moved K1 over to the left. So we're going to have some sort of difference over here. The other thing to note is that, again, I told you that the error function, when this goes to infinity, is going to be square root of pi over 2. So at infinity, now our concentration is going to be this value, and the integral will come out to be square root of pi over 2. So our K0 will turn out to be this, the difference between the walls over some constant that is pretty much needed to normalize the integral. So again, updating our general solution with both the constants, we get something that looks like this. This isn't the most useful form of the equation, so what I'm instead going to do is I'm going to move all the concentration terms on the left and this on the right. So now you should see, okay, we have that 2 over the square root of pi. Now you see that we do have a true error function on the right-hand side of the equation. And the error function, remember, since the variable up here is lambda, it's going to be the error function evaluated in terms of lambda. So at this point, we finally have a concentration profile. And the concentration profile will look like this. Written explicitly in terms of C, it'll look like this. Written as more commonly, you'll see it like this up here. Okay, so what does this actually mean? What does this complicated expression actually mean? Well, let's take a little bit of a look at it. So now, if you didn't care about the mathematics, now we're going to discuss the results of this final concentration profile. So initially we wanted to model what exactly is the behavior going on within this system over here. Well, what I did is I went into MATLAB and I started to model basically this equation. So I chose a fixed value of D, and I chose a fixed initial concentration and final concentration. And the plots I made, you'll see, will be dimensionless so that they're relatively easy to understand. So the results is that at some low time, I got the following profile. So on the x-axis, you'll see dimensionless z, and on the y-axis, you'll see dimensionless concentration. So 1 just represents hitting the end of the infinite slab, and the axis on the left-hand side is the high concentration, on the right-hand side is low concentration. So as you get further and further along into the infinite slab, your concentration is going to drop. Okay, we get this sort of exponential looking profile here. These values were taken, the y values were taken using a normal distribution table to evaluate for the error function, which your professor should show you how to use if you're going to be doing some example problems on this. At some later time, we see it look like this. So the first one is at maybe 5 minutes, and the second one was at maybe 10 minutes. So you see that the concentration profile is going to be changing as a function of time. At an even later time, which is now going to be in magenta, the concentration profile is looking like this. So this is at maybe 20 minutes. So this is at 5 minutes, this is at 10 minutes, this is at 20 minutes. If we look at our concentration profile when it's at 40 minutes, you'll see that this line is straightening out. This is now pretty much a straight line, which is exactly what we saw when we originally did thin film diffusion, steady state. If I increase this time to say 400 seconds, you'll say is that it's an even more dramatic straight line, but you see that the slope has been changing. It's no longer a straight line along here, it's a straight line along here. If I make it a very, very long time, say several thousand or a million seconds, you'll see that it's pretty much just a straight horizontal line. Okay, that's interesting. What exactly is happening here? Well, I'll explain to you. And the following comes from Cussler's text. When you have equilibrium, when the left hand and the right hand side have the same concentration, what you see is pretty much no change in the middle region. It's just going to be a straight flat line, which is again what we saw at very, very, very long time scales. The steady state one is what we saw the very first lecture for a thin film. So at some time period, basically you get that straight line and it's now a steady state concentration profile. This assumes that the left hand and the right hand concentrations are large enough, or I guess the volumes are large enough so that there's no significant concentration change over time. If you wait long enough, then there's some mass transfer to the point where these, I guess, edge values start moving closer in. So this will move downward and this will move upwards until they meet in the middle, and then you'll have this equilibrium. Early on, what you have is the unsteady state diffusion, where you see diffusion on the left-hand side, but you don't yet see diffusion happening on the right-hand side because molecules haven't been able to meet here yet. If the slab is infinitely long, then 10,000 miles out to the right, you're not going to have any effects from whatever's going on at the left. They're not going to see basically what's happening. It's like if there's a tsunami. Over here is at the front of the wave, they're seeing the tsunami, but over here, they're far enough out that they don't see the tsunami. Eventually the tsunami comes, and it wrecks them, which is what you see over here, and even longer time, this is well after the wave has crashed, that everything just tapers out to be equal. So to sum up what we're actually saying here, why do we care about the semi-infinite slab? Well, it's odd you have this relationship between time and space here. At incredibly short time scales, a thin film becomes an infinite slab, right? So even if your film is very, very thin, if you look at it at a very, very short time delay, what you'll see is unsteady state diffusion. So all thin films will have unsteady state behavior. You need to wait long enough so that you're in a steady state regime. You need to figure out when you're modeling the problem, if you're working for a company or so, if you could wait long enough for that steady state regime to come up. And furthermore, if you wait long enough, you're going to be at equilibrium and no longer in a steady state regime. Moreover, perhaps what's even more interesting is at large enough time scales, what we consider to be infinite slabs or very long slabs become thin films. So this entire process between thin film and infinite slab is dependent upon the time scales that you are looking at. These are really the two takeaway points of today's lecture. You should also know these diagrams over here. You need to understand how to use the normal distribution table to evaluate the error function, and pretty much you should be able to solve problems using this final concentration profile.